So in this paper, we deal with the few shot incremental learning problem, in which the model is supposed to learn incrementally, but with only a few training examples per class. Current incremental learning approaches are actually not suitable for this problem because they require the complete training set per class. To deal with this, we apply a cognitively inspired clustering technique on the images of each new class to get a set of centroids, which are then kept for later use instead of the actual images. To classify an image belonging to any of the classes learned so far, the centroids are used in a weighted voting scheme to get a predicted label. We further present a centroid reduction technique to cluster the centroids of the previous classes into a smaller set of centroids in case the system runs out of memory. So we test our approach on benchmark datasets like CVPR100, and it beats the state-of-the-art methods with huge margins for incremental learning. For few-shot incremental learning, again our approach beats the state-of-the-arts, even if they use complete training set per class, and our approach only uses like 5 or 10 training examples per class. Thank you.
Hello, I'd like to introduce you to the Stream51 image classification dataset. Instead of traditional image classification datasets, which train on thousands of independent images per object, we built a dataset made up of dozens of small snippets of videos. Training a classification model in this way forces the model to generalize from highly correlated images and approximates how real-time agents must learn to classify objects. In addition to streaming data, we also establish protocols for novel object identification by including novel classes in our evaluation set that are unseen during the training sequences. Existing streaming classification datasets have been small-scale, first-person view-oriented videos that lack diversity and do not establish protocols for novel class detection. Our dataset has 51 independent classes with videos taken in diverse and natural environments and baselines established for streaming novelty detection. Please download our paper for more details and experiment with the dataset yourself. Thank you.
Hello everyone, I'm Kengo Murata. I will present the overview of our work. In continual learning, a model learns each task step by step. However, the model suffers from the task performance degradation. Clearly, understanding the forgetting on the representations must help to understand the catastrophic forgetting. But such representation forgetting is mostly unknown. So, we propose new evaluation framework to understand the forgetting on the representations. In our framework, we firstly train the model on the continual learning setting, then we retrain it partially with offline setting. Lastly, we quantitatively evaluate representation forgetting using two metrics. These graphs show resulting F1 scores in our experiment, and you can see that the different task gets the highest score, thus the direction of task bias is different with the depth of the layer. That's all. If you get interested in our work, please join our interactive session. Thank you for listening.
Hello, I am Nicholas Guo, and I'm from the Australian National University. I would like to give a brief summary of our paper, M2SGD, Learning to Learn Important Weights. Neural networks are powerful models, but they are often large and computationally expensive. Pruning aims to lower both attributes. However, pruning could also be computationally intensive. This is because they often require a dense network to be retrained for multiple trials. In order to achieve efficient pruning, we propose to combine network pruning with learning to learn. In our paper, we have learned a neural optimization algorithm which automatically removes unnecessary weights. Thank you for listening, and please check our paper for more details.
Hi, my name is Saina. I'm a PhD student at UC Berkeley, and this is our joint work with Facebook AI Research Lab. Our goal in this work is to sequentially learn multiple tasks without forgetting them. And our solution is to split the common knowledge required to learn all tasks from the specific skills unique to each one. The intuition behind our approach is that we think learning a new task in a sequence should not start from scratch, but from the shared core knowledge among them. We introduce our approach as a hybrid continual learning algorithm that uses adversarial learning for disentangling task-specific and task-invariant features, and primarily relies on architecture growth to avoid forgetting, and if need be, uses experience replay to preserve the shared knowledge. Finally, we have extensively verified our method on a variety of datasets and benchmarks. You can read our full paper, and our code is also publicly released. Thank you for your attention.
This is a short video about our CVPR workshop paper StackNet. In the field of continual learning, researchers are trying to make neural networks conserve the previously learned knowledge, while absorbing the new knowledge. In this paper, we propose a method which intuitively uses the capacity of a network without degrading the performance of previous tasks. Our method works pretty similar to PACnet, but is much more intuitive since we separate tasks by simply stacking the filters. Many other works in this field have usually assumed that the prior knowledge of the input is known, and we all know that it's not how it works in the real world. So, in order to determine which group of parameters should be used, we propose a simple module named index module, which is a simplified version of generative replay. Our method shows comparable results as in this table. We recommend you to read our paper for more detailed information. Thank you.
Continual learning, which updates machine learning models according to streaming data, is increasingly needed in the dynamic systems. Previous approaches attempt to learn the knowledge class by class from scratch. However, they still suffer from severe accuracy drop and high computation costs. We propose a novel brain-inspired paradigm named acquisitive learning. Acquisitive learning starts from an elaborately selected model with pre-trained knowledge and then adapts it to new data using segmented training. The selection is achieved by injecting random noise to various inherited models for better model robustness, which promises higher accuracy in further knowledge acquisition. The combination of selective inherited model and knowledge acquisition reduces catastrophic forgetting by 10 times on C500 datasets. Benefiting from its high computation efficiency, the acquisitive learning enables online learning at the edge.